previous video, a Riemann sum can be expressed in sigma notation. Noting that sigma notation really is just the addition of whatever equation you want it to be. So, because we want to find the area of all the rectangles with Riemann sum, basically in summation notation, it would be the addition of all the area of the rectangles from k equals 1 or your lower bound to any n or upper bound. So you'll find that it's basically the area of one rectangle, the second rectangle, all the way until the last rectangle. Right Riemann sum can also be expressed a different way. Not just this formula, but also this one, because you could replace this x of k with a plus k times the delta x. As we learned in sequences, in order to find the next value, you have to add the different changes. So being that this is x sub 0, you have that it's basically the lower bound of our sigma notation. So x sub 0 would equal a. So that means x of 1 would just be a plus that delta x. And then x sub 2 would just equal a plus 2 times that delta x. So you just keep on adding that, and you'll find that whatever n value or whatever number of rectangles you want, the x would just equal a, or our initial or lower bound, plus that change in x times k, or however many number of rectangles that you want. So you can see that when you plug into the formula, you'll actually get the addition of the change in x times f of the initial start plus the change in x times whatever amount of rectangles you want. So I'll show a little example to make more sense of what this equation really means. These are also some helpful summation rules that you need to know in order to solve for the limit of the Riemann sum. Y equals t squared is represented from 0 to 8. So instead of the x variable, we'll be using a t in this example. So the first thing we always look for is going to be the delta x, or in this case the delta t, which equals to b minus a over n. So based on the equation that we're given and the bounds that we have, it's going to be 8 minus 0 over n, which gives you delta t is going to equal 8 over n. So something we also learn is that tk, or xk, equals a plus k times delta t. So based on the formula, once again, we're going to get that it's going to equal 0, which is our a, plus 8 over n times k. So we get tk equals 8k over n. As we learned before, the right Riemann sum in summation notation to be the summation, or the sum of the areas of the rectangle, which is f of x of k times delta x from k equals 1 to n. So we're going to replace what we know and what we solve for in terms of this formula. So we get the approximation of the area under the curve, or the right Riemann sum of whatever curve that we have, equals to the summation of f of 8k over n times 8 over n from k equals 1 to n. So instead of this f of 8k over n, we're going to replace it in terms of the equation. So we find that t squared is actually going to equal 8k over n squared. Because we have two variables right now, we have n and k, we're going to actually isolate the k value so that we can use the summation rules in order to find our equation in terms of n. So in this case, n is going to be a constant because it's not going to be the variable we're worrying about. So we're going to isolate k, and we get that it's going to be the summation of k squared. So recalling the summation rules that I mentioned before, the summation of k squared actually equals n times n plus 1 times 2n plus 1 over 6. So because we're trying to find the equation in terms of n, we're going to replace it. So after simplifying this value, we get that it's going to equal 512 over n to the third power times this summation of k value, k squared value. And after simplifying, we're going to get that the Riemann sum formula in terms of n, using the summation notation, is equal to 1024 over 6 plus 1536 over 6n plus 512 over 6n squared. Once we find the Riemann sum formula, we can actually find the area under the curve, actually, because the limit as n approaches infinity of these rectangles get infinitely smaller and more accurate, closer approximation of the area. You actually get the real area by finding the limit as n approaches infinity of the Riemann sum, which in this case is expressed in sigma notation, and it equals the definite integral of f of x from a to b, which I'll show you later why. So back to the original question, using the Riemann sum formula that we found, we find that the limit as n approaches infinity of this formula is actually going to equal 1024 over 6. How I got that answer was that if you find the limit of this value, it's going to stay the same. If you find the limit as n approaches infinity here and here, these values actually approximate 0. Like an example, 1 over infinity, you know, will be approaching 0. So actually, the area under the curve is going to be about 170.67. And we can actually check that, since we can find the definite integral. So going back to the original equation, t squared from 0 to 8, we can see that once we plug it in to the definite integral formula, you can see that from 0 to 8, t squared dt, and once you solve, you actually get the same number. You get 170 and 2 over 3, which is exactly the same amount we got from finding the limit of the Riemann sum. I hope my video was helpful in allowing you to understand how the limit of the Riemann sum equates to the definite integral. Thanks for watching.